The research paper's first page discusses transcription-only supervised text spotting, a challenging task that aims to locate each transcription in seen text images without location annotations. This is formulated as a weakly supervised cross-modality contrastive learning problem. The authors propose a model called WeCromCL, which conducts atomistic contrastive learning to model character-wise appearance consistency between a text transcription and its correlated region in a scene image. This allows for detecting anchor points for transcriptions in a weakly supervised manner. The detected anchor points guide the learning of text spotting. The model is evaluated on 4 challenging benchmarks, demonstrating its superior performance over other methods. The authors highlight the limitation of existing fully supervised learning methods and propose a novel approach to address this limitation. The authors introduce WeCromCL, a method that conducts atomistic contrastive learning for transcription-only supervised text spotting. This approach differs from existing methods, such as TCM, OCLIP, and VLPT, which require full supervision with text polygon annotations or rely on auxiliary tasks for optimization. WeCromCL operates in a weakly supervised manner, requiring only text transcriptions without text location annotations, significantly reducing the annotation overhead. The authors highlight the challenges of transcription-only supervised text spotting, particularly the difficulty of locating text transcriptions in seen text images without annotated text boundaries. They also discuss existing methods, including NPTS and TOS, which have limitations such as arduous optimizing convergence and high computational requirements. The research paper introduces a novel approach to transcription-only supervised text spotting, divided into 2 stages: weakly supervised text detection and single-point text spotting. The authors propose WeCromCL, a method that utilizes weakly supervised cross-modality contrastive learning to detect anchor points for transcriptions in scene images without location annotations. This method forms the basis for learning a single-point supervised text spotter, which relies on only one single point instead of text boundaries as detection supervision. WeCromCL is designed to learn an effective cross-modality character-wise consistency metric between a transcription and its visual appearance in a scene image, thereby detecting correlated image regions for the transcription without annotated text boundaries. The rationale behind this approach is that a transcription acts as a cluster center, associating all matched images containing it, and the model is optimized to learn similar appearance patterns for this transcription among all associated images. The authors also leverage the predicted anchor points by WeCromCL as pseudo-location labels to learn an effective single-point supervised text spotter adapted from SRSTSv2, a state-of-the-art text spotter. By integrating the proposed WeCromCL and the learned single-point text spotter, the researchers construct a powerful transcription-only supervised text spotting system. This work significantly contributes to the field of text spotting by formulating and investigating the weakly supervised atomistic contrastive learning problem between image and text modalities, proposing a simple yet effective method for it, and demonstrating its effectiveness in real-world applications. The research by Jingjing Wu et al. Introduces a novel system for transcription-only supervised text spotting, exhibiting enhanced performance on 4 demanding benchmarks. This approach diverges from existing methods by focusing on modeling character-wise appearance similarity between text transcriptions and their correlated regions in scene images. The system consists of a 2-stage process: detecting anchor points for transcriptions and conducting text spotting. This methodology differs from others, which often require precise boundaries for supervision or use additional annotated data for training. The author's approach aims to simplify the transcription-only supervised text recognition problem, presenting a promising direction in the field of text spotting. The paper introduces a groundbreaking approach to transcription-only supervised text spotting, overcoming the limitations of previous methods by breaking down the task into 2 stages. The first stage involves detecting anchor points for each transcription using a weakly supervised cross-modality contrastive learning framework, referred to as WeCromCL. This framework is designed to learn the correlated visual features between transcriptions and their image regions. The second stage utilizes the obtained anchor points as pseudo-location labels for text spotting under single-point supervision. The paper's architecture is detailed in Figure 2, showcasing the key components and their roles in the process. It highlights the challenges in detecting anchor points without transcription location annotations and the importance of predicting precision in this step for the overall performance of text spotting. This novel approach has the potential to significantly enhance the efficiency and accuracy of text spotting in various applications. The authors formulate the task of transcription-only supervised text spotting as a contrastive learning problem, where the goal is to estimate the location of each transcription in a scene image without annotated text locations. This is achieved by optimizing a contrastive learning model, denoted as F, which transforms an image I and a text description T into a correlation C, as shown in equation 1. In the context of weakly supervised atomistic contrastive learning, the correlation C is represented as the element-wise multiplication of an activation map M and the image I, with the text transcription T, as shown in equation 2. The activation map M, whose elements are binary values indicating whether a pixel is associated with the transcription T, is estimated without ground truth labels. This setting is referred to as weakly supervised atomistic contrastive learning between image and text modalities. The authors identified two crucial challenges in formulating the detection of transcription in an image as weakly supervised atomistic contrastive learning. First, effective modeling of F requires precise estimation of the activation map M in weakly supervised learning without ground truth. Second, unlike typical cross-modality contrastive learning, the goal is to learn the atomistic correlation between a text transcription and its visual appearance in the correlated region in the scene image. To address these challenges, the authors propose WeCromCL, a simple yet effective model for weakly supervised atomistic contrastive learning. WeCromCL detects an anchor point for each text transcription to locate its correlated region in the scene image, serving as a pseudo-location label for optimizing the text spotter in the second stage. The model follows a weakly supervised atomistic cross-modality contrastive learning framework, taking a text transcription T and an image I as input, and predicting the correlation C between them, as well as the activation map M, where the highly activated region corresponds to the associated image region for the text transcription and is identified as the anchor point. As shown in Figure 2, WeCromCL employs an image encoder and a text encoder to learn latent embeddings for the input image and text, similar to CLIP. The WeCromCL model addresses the challenges in cross-modality contrastive learning by introducing a soft modeling mechanism for learning the activation map and a character-wise text encoder. This approach enables the learning of character-wise appearance similarity and optimizes the model through atomistic cross-modality contrastive learning. The image encoder employs BIFPN and a deformable transformer encoder to extract multiscale features. The text encoder, similar to OCLIP, focuses on character-wise appearance consistency and includes positional embeddings to capture temporal sequence information. The model learns to fuse these embeddings through a transformer encoder, resulting in an average text embedding. The soft modeling mechanism measures the appearance correlation between the transcription and each pixel of the input image using cosine similarity in a projected feature space. This approach allows the model to learn character-wise appearance similarity and optimizes the model through atomistic cross-modality contrastive learning. The WeCromCL framework, a cross-modality contrastive learning model, leverages image-text pairs to enhance visual and textual feature learning. It introduces a novel method for learning activation maps that highlight image regions relevant to their textual descriptions through a soft modeling approach. This approach utilizes learnable transformation matrices, resulting in continuous values between 0, 1, indicating higher response to the transcription. The activation map is then used to aggregate correlated features in the image to the text transcription, effectively performing cross-modality cross-attention operation. The authors also propose a cross-modality contrastive learning strategy by negative sample mining, where they construct negative pairs in two ways: image-to-text and text-to-image constructions. The loss function for this strategy is designed to maximize the cosine similarity of positive pairs while minimizing the similarity of negative pairs. The proposed WeCromCL framework aims to optimize all modules jointly and enhance the learning of visual and textual features. The use of a negative sample mining scheme introduces more challenging negative pairs and further improves the robustness of the model. This research contributes to the advancement of image-text understanding and generation tasks in various applications, offering a promising approach for improving the performance of multimodal learning models. WeCromCL 9 enhances modeling robustness by applying a hard sample mining scheme that selects more similar but unpaired transcriptions to construct hard negative pairs. This scheme, along with a simpler method of randomly selecting unpaired transcriptions, can yield similar performance gains. The loss function, Li2t, computes the cosine similarity between feature vectors of image and transcription pairs and their augmented negative pairs. Integrating these losses, the loss for a batch of n images is LCM, which learns an effective cross-modality character-wise consistency metric between a transcription and the visual appearance in a scene image. This approach detects correlated regions in images to transcriptions in a weakly supervised mode. The rationale behind WeCromCL is that a transcription acts as a cluster center, associating all paired images with it, and the model is optimized to learn similar appearance patterns regarding this transcription among all paired images. The optimization by minimizing similarity between negative pairs guides the model to learn discriminative appearance patterns for each transcription, preventing model collapse to a uniform pattern for different transcriptions. The most activated position in an activation map M learned from WeCromCL is identified as the anchor point for the corresponding transcription, used as a pseudo-location label for learning the text spotter in the second stage. The authors instantiate their proposed text spotter using SPTS and SRSTSA, leveraging the predicted anchor points by WeCromCL as pseudo-location labels to train SPTS. This approach formulates text spotting as a sequence prediction task, with SPTS performance reflecting WeCromCL's accuracy. For SRSTSA, they adapted to rely on a single point during training, providing adaptation details in the supplementary material. Combining WeCromCL and SRSTSA, they construct a powerful system for transcription-only supervised text spotting. The experimental setup includes benchmarks such as ICDAR 2013, ICDAR 2015, total text, and CTW 1500. With evaluation metrics being single point and edit distance, following SPTS. Implementation details are provided, including joint training set use and pseudo-location labels from WeCromCL for supervision in the text spotting stage. The authors of the study conduct an ablation analysis to evaluate the efficacy of their proposed method, WeCromCL, in text recognition tasks. This involves comparing the character-wise text encoder of WeCromCL with the token-wise text encoder of CLIP, which focuses on learning the semantics of the entire text. The results in Table 1 reveal that the character-wise text encoder significantly outperforms the token-wise encoder of CLIP on all three metrics. This suggests that encoding text at the character level facilitates the learning of character-level correlations between a transcription and its visual representation in the image. Furthermore, the authors investigate the effectiveness of the proposed negative sample mining scheme in WeCromCL by comparing the performance of two variants of WeCromCL: training with the negative sample mining scheme and without it. The results in Table 2 demonstrate that the negative sample mining scheme yields substantial performance gains, particularly improving the FM measure on the training and test set of CTW 1500 by 7.2% and 10.2%, respectively. The quantitative evaluation of transcription detection, as shown in Table 1 and Table 2, indicates that the obtained pseudo-labels for the training set are accurate and can significantly enhance the performance of the model. This highlights the importance of the character-wise text encoder and the negative sample mining scheme in improving the transcription detection capabilities of WeCromCL. The novel atomistic contrastive learning approach, WeCromCL, is compared with the holistic contrastive learning method, OCLIP, in the context of weakly supervised text detection. Table 3 presents a comprehensive comparison between the two approaches, showcasing the superiority of WeCromCL. Specifically, WeCromCL achieves higher precision, recall, and FM measure scores across various benchmarks, including ICDAR 2013, ICDAR 2015, total text, and CTW 1500. Notably, WeCromCL outperforms OCLIP by a significant margin, with FMeasure scores of 93.2%, 88.6%, 84.3%, and 66.3% on the training set, and 90.5%, 83.4%, 80.3%, and 77.7% on the test set, respectively. This highlights the effectiveness of atomistic contrastive learning in capturing fine-grained text features. Furthermore, WeCromCL is used to generate pseudo-location labels, which are then employed to train SPTS, a single-point text spotter. Table 4 compares the performance of WeCromCL plus SPTS with NPTS, an adapted transcription-only supervised variant of SPTS. The results demonstrate that WeCromCL plus SPTS surpasses NPTS in all evaluation dimensions, particularly in scenarios without lexicons or with a generic lexicon. The comparison between WeCromCL and OCLIP is attributed to the difference in their contrastive learning approaches. OCLIP performs holistic cross-modality contrastive learning between an entire scene image and all text appearing in the image, whereas WeCromCL employs atomistic contrastive learning, focusing on individual characters. The superiority of WeCromCL is evident, as it achieves better performance despite only being trained on the training set. WeCromCL, a novel approach, significantly enhances the performance of fully supervised spotting methods by generating pseudo-location labels from text-image pairs without annotations. A visual comparison of attention maps between WeCromCL plus SPTS and NPTS demonstrates the superiority of WeCromCL. This is achieved through its ability to create accurate pseudo-labels, which in turn improve the performance of fully supervised single-point spotter. The pre-training and fine-tuning process of SRSTS-v2 on synthetic and real datasets is also explored. Results show that WeCromCL can substantially enhance recognition performance, particularly with sufficient pseudo-labeled data. The effectiveness of WeCromCL is attributed to its capacity to leverage text-image pairs, generating high-quality pseudo-labels that augment the training data. The visual attention maps provide insight into the spotting process, highlighting the regions of interest where WeCromCL excels. By comparing the attention maps of WeCromCL plus SPTS and NPTS, the superiority of WeCromCL is evident, showcasing its ability to accurately identify and localize targets. The findings suggest that WeCromCL can be a valuable tool for improving the performance of fully supervised spotting methods, especially in scenarios where annotated data is limited. Furthermore, the results imply that the quality of pseudo-labeled data significantly impacts recognition performance, emphasizing the importance of generating high-quality pseudo-labels. The analysis presented focuses on transcription-only supervised text spotting methods, particularly the author's optimized system, WeCromCL plus SRSTSA. Figure 5 visualizes the performance on ICDAR 2013, ICDAR 2015, total text, and CTW1500 datasets, with green, plus, symbols representing estimated anchor points and blue dots denoting sampled points. Table 5 provides quantitative results for various text spotting methods, including fully supervised, semi-supervised, and transcription-only supervised approaches. The author's optimized system outperforms other transcription-only supervised methods in terms of performance metrics such as single-point and edit distance metrics, surpassing NPTS and TOS by 16.4% and 9.2% on ICDAR 2015 when evaluated with a general lexicon. The discussion also highlights the gap between synthetic and real-world data, which is significantly improved when fine-tuned on real-world data pseudo-labeled with the WeCromCL method without introducing human annotation costs, emphasizing the effectiveness of the proposed method in bridging this gap for transcription-only supervised text spotting tasks. The research on WeCromCL 15 focuses on the development of a semi-supervised text spotter, TTS-weak, which outperforms other methods by 5% and 6.5% in the metric of none. The system utilizes pseudo-location labels generated by WeCromCL for training. Figure 5 visualizes the spotting results, showcasing effectiveness in handling challenging scenarios like tiny, fuzzy, curved, and long text. The approach decomposes transcription-only supervised text spotting into two stages: detecting anchor points and conducting text spotting guided by these points. The detection of anchor points is formulated as a weakly supervised atomistic contrastive learning problem across modalities, with WeCromCL devised for it. Extensive experiments demonstrate the effectiveness of the proposed method, although it requires high-resolution images for detecting small texts, which is a limitation. The research paper examines the application of machine learning algorithms in predicting climate change impacts on global food systems. It highlights the importance of integrating climate models with agricultural data to enhance the accuracy of predictions. The study focuses on the use of neural networks to analyze historical climate data and agricultural productivity trends, aiming to identify vulnerable regions and optimize resource allocation for sustainable food production. The Masked Text Spotter v3 proposes a segmentation proposal network for robust scene text spotting, showcasing advancements in the field. This is followed by the TextBoxes plus and TextBoxes detectors, which focus on fast text detection using a single deep neural network. The concept of focal loss for dense object detection is introduced, leading to the discussion of ABCNet and its variants for real-time scene text spotting. Curved scene text detection and the use of adaptive Bézier curve networks are also highlighted. The SPTS v2, a single-point scene text spotting approach, concludes the discussion. Throughout, the technical aspects are emphasized, focusing on novel ideas, significant findings, and important arguments presented in these papers. Scene text spotting has witnessed significant advancements in recent years, with a focus on end-to-end spotting of arbitrarily shaped text, decoupling recognition from detection, and vision language pre-training approaches. PAN++, proposed by Wang et al. In 2021, is an efficient and accurate method for end-to-end spotting of arbitrarily shaped text. Wu et al. Introduced decoupled yet collaborative detection and recognition approaches in 2022 and 2023, enabling single-shot self-reliant scene text spotting. Shui et al.'s 2022 work presented a weakly supervised vision language pre-training approach for scene text detection and spotting, emphasizing the importance of language in scene text understanding. Other notable contributions include Yang et al.'s 2022 proposal of vision language pre-training with triple contrastive learning, and Yi et al.'s 2023 introduction of Deep Solo, a transformer decoder-based method for text spotting. Yu et al. Demonstrated in 2023 the effectiveness of converting a clip model into a scene text detector, while Zhang et al. Developed text spotting transformers in 2022. Zhu et al.'s 2022 work presented deformable DETR, a deformable transformer-based approach for end-to-end object detection. Collectively, these works highlight the significance of integrating detection and recognition, leveraging vision language pre-training, and exploring novel architectures for scene text spotting. The importance of considering arbitrarily shaped text, language understanding, and efficient detection and recognition mechanisms in scene text spotting systems is underscored. The WeCromCL system is instantiated by adapting SRSTS to SRSTSA, which consists of an image encoder, anchor estimator, sampling module, and recognition module. The anchor estimator predicts anchor points for each text transcription, while the sampling module performs sampling around each anchor and provides the recognition module with sampled features for text decoding. Three major modifications are made to adapt SRSTS to SRSTSA. First, the detection branch using text boundaries is dropped. Second, practical techniques from Deep Solo, including the image encoder, data augmentation, and optimization strategies, are incorporated into SRSTSA. Third, the loss function for the anchor estimator is modified from dice loss to focal loss to adapt to the supervision variation from text boundaries to anchor points. The focal loss function is used to optimize the parameters of the anchor estimator, which learns a confidence map to indicate the probability of each pixel being an anchor. The focal loss function is defined as equation 1, where alpha and gamma are weighting factors. CGT is the pseudo ground truth for the confidence map constructed from the obtained anchor point, and C is the confidence map generated by the anchor estimator. WeCromCL is integrated with SRSTSA to obtain an optimized system for transcription-only supervised text spotting. The implementation details of WeCromCL involve pre-training on synthetic datasets for 200,000 steps with a batch size of 16, followed by fine-tuning on the training set of each dataset for 80,000 steps with a batch size of 4. Data augmentation strategies, including random resizing, are conducted during training. In the context of scene text recognition, researchers have developed a novel method for generating pseudo-location labels using text-only supervision, known as WeCromCL. This approach leverages weak supervision to improve the accuracy and efficiency of text spotting models. The method involves pre-training a text spotter on a joint dataset containing curved synthetic dataset, ICDAR 2017 MLT, ICDAR 2013, ICDAR 2015, and total text with pseudo-location labels for 425,000 steps. For word-level benchmarks, the text spotter is fine-tuned on the training set of specific benchmarks for 3,000 steps. For CTW 1500, line-level text transcriptions of synth text are used to generate line-level pseudo-location labels, and the text spotter is further trained for 100,000 steps based on these labels. Finally, the pre-trained model is fine-tuned on CTW 1500 training set for 20,000 steps. The authors employ Atom as an optimizer, with the learning rate set the same as Deep Solo, and use the same data augmentation except for random cropping operation being removed. In the testing phase, the shorter side of input images is resized to 864, 864, 1440, and 576 for ICDAR 2013. ICDAR 2015, total text, and CTW 1500, respectively. Ablation studies are conducted to compare the pseudo-label quality on ICDAR 2015. The results show that WeCromCL outperforms other keypoint localization, pseudo-labeling methods such as OCLIP and NPTS, with a precision, recall, and F1 score of 91.4%, 86.0%, and 88.6%, respectively. This demonstrates the efficacy of WeCromCL in generating high-quality pseudo-labels using text-only supervision, which significantly improves the final spotting performance. The supplementary page provides an in-depth analysis of the spotting results under various pseudo-label generation methods and ablation conditions on the ICDAR 2015 dataset. It showcases the efficacy of the proposed method, particularly in text-only and single-point annotations. A comparative table illustrates the accuracy of the proposed method against ground truth and perturbed anchor points, demonstrating the high quality of the pseudo-labels generated. The results underscore the significance of detailed positional information, leading to a performance gap between fully supervised methods. The section concludes by expressing the intent to explore methods for obtaining high-quality pseudo-labels at the box level. The WeCromCL model, a deep neural network designed for text localization in images, utilizes activation maps to visualize its functionality. These maps pinpoint regions of high activation, corresponding to specific text transcriptions within input images. The model's robustness is demonstrated in Figure 1, where it effectively handles complex cases, including text with artistic fonts, curved text, long text, and small text. Each input image and its corresponding text transcription yield an activation map, identifying the anchor point for the given transcription. This showcases the model's capacity to accurately detect and locate text within diverse contexts, such as commercial signs, historical information, and artistic expressions. The activation maps provide valuable insights into the model's decision-making process, highlighting the regions that contribute most significantly to text localization. By visualizing the model's internal workings, researchers can gain a deeper understanding of its strengths and limitations, ultimately informing improvements to its architecture and performance. The WeCromCL method's supplementary materials focus on visualizing text spotting results and the effectiveness of the proposed transcription-only supervised text spotter. Figure 2 demonstrates the performance on 4 benchmarks: ICDAR 2013, ICDAR 2015, total text, and CTW 1500. Green, plus, symbols represent estimated anchor points, while blue dots denote sampled points. The results show the WeCromCL method successfully locating text regions given a text query, even for small and fuzzy text within images. Anchor points from activation maps are used as pseudo-location labels to supervise the text spotter's learning in the text spotting stage. This supervision enables satisfactory performance in challenging cases like tiny text, fuzzy text, curved text, and long text. The visualization intuitively demonstrates the effectiveness and robustness of the proposed text spotter, highlighting the significance of pseudo-location labels from WeCromCL.